The plan for today is to continue talking about robust control. And I mentioned already 3 different subdomains of robust control, which are kind of less popular than the main one, which is related more to norms of different systems. So we mentioned polynomial type of robust control, where you have interval polynomials and you have all kinds of expansions to interval polynomials as well. And then we talked about Kharitonov theorem related to that polynomial thing. Then we talked about why this is correct based on the zero exclusion principle. And then we moved to all stabilizing controllers, where we showed that you actually can develop all possible stabilizing controllers. And this will give you kind of flexibility to work with systems. And I haven't even mentioned why having all of the stabilizing controllers is good for you, because why would you even want to have more than one stabilizing controller? So if you have some particular plan, it's okay to have one controller, which you just put it in series or wherever in the feedback, and then you solve the problem, right? You're controlling the system. You don't need millions of different controllers which will stabilize your system. But based on that theory of all stabilizing controllers, you technically can develop families of controllers, and based on the families of controllers, you can control families of plans, which means if plant has particular uncertainty, so you don't know exactly the parameters of the plant, so you can design controllers for all of these plants and all of the possible controllers, and from them to select that subset which is stabilizing that entire family. So it's practically only first step in robust control part of the stabilization of family of plants, and not specifically to stabilize all of the plants. Okay. I'm just not getting too far away into that theme. And then we saw the example. We saw that we can do the same thing with state space representations. I'm kind of skipping past through all of these topics because this is just material for you to be aware of, let's say. You don't have to know details of it. You just need to be aware that all these things exist. And now today we are moving to the main topic of robust control. Maybe not main topic, but most developed topic. I would say most popular part and biggest part of robust control. And again, I'm not getting into the actual robust control here, but giving you mostly terminology and what things might be useful for you to understand later literature on robust control if you want to read it, okay, for whatever reason. So most of that theory is based on norms of signals and norms of systems. And you can define norms in multiple different ways. You have millions of different possible norms, and you can develop your own norms as well. You can add to the library of norms whatever you want. But norm is any function which satisfies 4 different conditions. Before I mentioned these conditions in this course, but I kind of skipped through that and haven't officially defined what norm is, right? But norm is some given function, which means it takes potentially some vector or function or any other object and converts it into a number. Now, this number, first of all, should be not negative, which means 0 or positive. It's real number, which is non-negative number. Okay, so this is rule number 1 here. So this is how I write norms, is double lines on both sides. So norm of particular signal u or vector u or any other object u, okay? So it could be practically vector of numbers like in linear algebra. It could be infinite number of numbers, which is like entire function. I can define it to different kind of objects or subjects. So that norm of u must be larger or equal to 0 by definition. This is what defines norm in general. It will be 0 only if that object is 0, which means it could be vector of zeros, it could be matrix of zeros, it could be function which is pure 0 for all times, okay? Or it could be a bunch of points which are all zeros. It could be all kinds of things which are all 0. And technically speaking, you define what 0 is for your particular object, because if your objects are not numerical objects like we used to handle, like all of the numerical vectors or algebra or functions, calculus, all these areas, you can define norms for any objects, and then you need to define what zero means for you, for that object, okay? And it could be practically anything. So it's very abstract definition of norm, okay? It fits anything, any possible object. So for value zero, you get norm zero. For norm zero, you must have that value zero. Okay, it's if and only if. This is the second rule. Third rule, third property, I would say, is for all scalar values a, if you multiply that a by that object, and again, if this object is not numerical object, you need to define what it even means to multiply scalar or number by your object. So we defined, for example, multiplication of scalar by vector. We multiplied multiplication of scalar by function. We multiplied what is scalar multiplied by matrix. Okay, and now you have, for example, tensor, you can multiply scalar by tensor. But now you have like space of chairs and tables, define what it means to multiply 5 by chairs, right? So you can define whatever you want it to be, okay? But you need to be consistent with your definitions. This is the point. So if you have something inside the norm, so norm of multiplication of scalar by some object that you have is absolute value of that scalar multiplied by norm of that object, which means you can take scalar outside of the norm, but with absolute value, because it must be positive. Okay, norm is defined to be positive always, not negative. Okay, it will be zero, but mostly positive, right? This is rule number 3. And this is the most famous part here, which is called triangle inequality, which is saying that norm of the sum of two objects equal to or equal or smaller than each one of them when you add them together. And you can think about norm also as distance in a way, okay? So it's like distance where you have two vectors u plus v. So the distance between u plus v is always smaller than sum of the radiuses for each vector. If you're thinking about vectors, like you have two vectors, u and v, the sum will look something like that, like parallelogram rule, right? This will be u plus v. So u plus v is clearly shorter or equal to u plus v lengths, right? For any two vectors. And they are equal only when they are collinear, looking in the same direction. Like if u and v looking in the same direction, if u would be that direction and v would be that direction, then the sum would be something like that, right? Which means the length will be actual sum of two lengths. This is the only case when they are looking in the same direction. Same thing with norms. You have cases where it is equal, so norm of the sum equal to the sum of norms, but it's only when the vectors are collinear in a way, okay? This is even how you can define collinearity of the vectors where they align in the same direction. Now, this is how we define norms for our signals, which means if you have input u or output y or any other state, for each one of the states or outputs or inputs, you can define norm of that input, and this will be positive or zero value, which will describe size of that vector in a way. So norm, you can think about that as size, philosophically. Okay, this is size, and size could be defined in multiple different ways. You can define size as particular Euclidean length or some other length. Let's say you have something curvy, okay? So would you define size as distance between the two extreme points or length of that curve? You can define in multiple different ways. You have geodesic distance, you have Euclidean distance, you have city block distance, you have all kinds of distances, okay? It's not uniquely defined. You need to define what you mean by distance, and norms the same thing. So these are our signal norms, which are most popular in the controls and robust control in general. First of all is L1 norm, or one norm, okay? One norm is integral on that signal absolute value from minus infinity to plus infinity in time. Okay, so it's like as a function of time. Obviously, U is a function of time. So norm one for that signal, and pay attention now, it's signal, it's not system. It's actual signal, it's U of t. So it's a function of time, some function of time. So what does that say? What is the meaning of that thing? So it's integral from minus infinity to plus infinity, absolute value of that function. So what is that? Calculus. What is integral on absolute value of signal? Or any function? Area under the curve. This is area under the curve. Okay, so norm one, the meaning of norm one, you're just measuring absolute area under the curve, which means in calculus, sometimes you measure areas as negative areas, right? So if you have negative function, you can say that this is negative area. But this is rectified function, which means you're flipping all of the areas up and you're measuring absolute area, like total area under the plot between the x-axis and the function. So you have all of that area as positive. Positive and negative will be counted as positive, and you're adding them all up. Now, what would be that area if the signal is periodic, for example? For any periodic signal, which means it's like starts at minus infinity, like think about sine wave or any other periodic signal. Like what would be area under the plot? This is not a tricky question. Area under the plot, 0. Positive area. Like it's flipped, it's rectified sign. It's all positive. So you're taking that sign and flipping it like that. Computing that area.
Is it total area under
Total area.
Yes.
It's from minus infinity to plus infinity.
Infinite.
Infinite. So for any periodic signal, no matter what signal you take, it doesn't matter. If signal is periodic, which means it starts at minus infinity and goes to plus infinity, you'll have more and more area added forever, right? Which means that area must be infinity. So norm one is always infinity for all periodic signals, okay? Same thing which happens with energy of the signal, right? Now, so what is that norm two, which is integral from minus infinity to plus infinity? Now, same thing squared, dt and square root of the integral. So what is that? What is integral of u squared? We talked about that recently.
Area under the curve.
Area under the squared curve. So how is that called in signals? So we talked about like integral of y squared plus rho u squared. So what that was? It was cost function, but cost function of what? Like it's weighted sum of what? Of energies. There's a signal energy. Okay. Why do we need absolute value here if it is squared? Squared is always positive, right? Why do you need absolute value? What is the only case where you need absolute value where you're squaring something? This is for complex functions as well. So it's defined not only for real functions, you expanding the definition for complex functions as well. So you could be complex function of any kind. Okay, just taking absolute value of that and then it becomes real numbers, real function. Okay, so practically speaking, this is square root of energy of the signal. This is what 2 norm is, or it's also called L2. So this is second very popular type of norm for signals. All right, it's just energy of the signal. This is its norm. Now, infinity norm, which is also very popular, is defined as supremum of absolute value of that function. So what is supremum? Again, calculus course. Have you learned in calculus course what supremum is? This is kind of maximum, but not exactly. This is kind of boundary on the maximum, not exactly maximum. So here's the thing. If your function has particular maximum, which means point where the function is maximal, okay, then supremum equals maximum. Okay, this is supremum and maximum, then the same. But not all functions achieve particular maximum. Sometimes they arrive asymptotically to their maximum. Think about arctangent's function, for example. Okay, so it would look like that. So we'll have some function which is going like that, and then asymptotically achieving maximum only at infinity. So it never actually achieves pi half, right? It just approaches pi half, but never achieves pi half. So you cannot say that maximum of the function is pi half, because then I will ask you, like, for which input, for which argument, okay? And you do not have that argument. This argument is infinity, practically speaking. It achieves that pi half at infinity. So this value of pi half is called supremum, not maximum, for that type of functions. So if you would have function which has some maximum, okay, so this would be max equal to supremum. But here supremum is not maximum because you never get to that maximum. So supremum is kind of another word for maximum, but for broader category of functions. Some functions do not have maximum officially. And you can think about it as maximum, but it's not like arctangent function has no maximum. Because you cannot say what argument provides you that maximum, right? It's infinity. But it has supremum. So the supremum says practically broader speaking maximum. Okay. So the maximum of that thing, what is that? So you have some function, which is whatever it is, changing somehow in time. So what is that maximum? What is the meaning of that maximum?
Is it the sum of each and every set?
No, it's like for a particular t. You're looking for maximum of that function, absolute value of that function. What is that? What is the maximum of that function?
Will be the high point of the one.
This is the point. This is your maximum. But can you explain in other words what that maximum means in terms of function? What would be your algorithm for looking for that maximum? You are looking for maximal deviation from zero for your given function, okay? So this point is where the function is farther away from the axis as possible. It could be positive or it could be negative. It could be maximum could be here, okay? It's also okay. Okay, this is the maximum of that function. It's maximum deviation from the function. So this is the meaning of that supremum. Where is the maximum deviation from that function? This is non-infinity. Why is that called non-infinity norm? Like, think about these things. Can you expand that to p norm? So this is 1, p equal to 2, and p equal infinity, having one formula for all of them together. Can you generalize these two formulas into p norm, where instead of 1, 2, 3, 4, 5, 6, infinity, you'll have general p norm, which is, by the way, also called, I believe, Minkowski norm. So what is the difference between these two? So this is to the power of 1 root 1, right? This is squared root 1/2, okay? For 3, it will be cubed root 1/3, and so on. Then you will have 100 root 100, okay? Radical, or whatever it's called, right? Now, what will be the limit of that thing when that p, which is here p, and here is 1 divided by p, goes to infinity? It will be exactly that thing. So when p goes to infinity, which means you're making that u to the power of infinity, absolute value of u to the power of infinity, integral on that entire thing, and then root of infinity, the limit will be exactly that. And you can prove that. This is why it's called norm of infinity, because you can generalize it to any p. But these are 3 which are typically used in practice, in signals. Any questions on that part? Because now we are going into more difficult things. Norms of systems. They are kind of similar, but not exact. So norms of systems, you can think about them as particular kind of game of the system for a particular purposes. So here's how it looks like. We have, again, 3 different popular norms, and you can have more, but these are 3 typical ones. And especially you'll hear a lot about H infinity norm, because H infinity is super popular in all of the robust control, all of the H infinity series, robust controller design in H infinity, and you have plenty of materials on H infinity. If you kind of type H infinity in Google, it will throw you like thousands and thousands of papers, tutorials, and what's not. Okay, so let's see what these things are. So let's say you have some given system G of S, transfer function with impulse response G of T, like capital G and regular G. Now, H1 norm is integral on that impulse response, which means you're thinking about impulse response as signal and doing just L1 norm on that impulse response. So what is the connection between impulse response and transfer function? Do you remember that? How you convert one into another. You have impulse response representation of your system. You have LTI system with impulse response G of T. How do you get to G of S? We are at the beginning of this course. Any ideas how to get from G of T to G of S? They have even the same name. This is just Laplace transform. You're doing Laplace transform of G of T, you get G of S. Okay, so this is a connection. So you have transfer function G of S, you can do inverse Laplace transform to get G of T to compute that thing, which is not too complicated to compute. Okay, and then you get norm 1 of your system. And we will see why we need all of these norms later. G2 is same thing with the square of the impulse response. Okay. And same thing you can do actually to the P norm. Okay, but now for systems it's called H norms. H1, H2, H infinity, and so on. But for H2 and H infinity, we have also other representations directly using transfer function instead of using impulse response, which is inverse Laplace transform of transfer function. Okay. Why is that? Because this thing is just energy of that signal square root of energy, technically speaking, right? But you have Parseval's theorem, which says that energy in time and energy in frequency are the same, right? Remember that theorem from signals and systems, Parseval's theorem, which says that energy in time and energy in frequency are the same, which means this is how you measure actually all of the Fourier transforms, where you have, you're doing Fourier transform of your signal, so you can find amplitudes of your sinusoidal components based on Fourier transform. Why? Because sum of all of the coefficients, like complex coefficients, absolute values squared, are exactly your power of the signal in time domain. So doing that technically integral on your function squared is the same as summing all of the coefficients of the complex Fourier transform squared, absolute values, okay? So this is the same thing, this Perceval theorem. So that's exactly what this thing is stating here. Up to a coefficient, of course, so you need 1 divided by 2 pi coefficient. So Perceval theorem states that you can compute the same norm using directly replacing S by J omega and computing that type of integral, okay, in S, or in that case in omega, okay, on J omega axis. So that's Perceval theorem. And then you obviously need to take square root because you have square root here of that energy. All right, so that's how you do H2. And we have even better rule for that, how to compute it. We will do that on the next slide. But before that, I want to define also H infinity norm, which is the most popular norm in this domain, okay? And H infinity norm is supremum on all omegas of G of J omega. What is the meaning of that thing? So what is that? Absolute value of G of J omega. You saw that multiple times by now. This is maximum of what? Now we have names for all of that. This is peak of body diagram. So absolute value is magnitude of the transfer function, right? So how do you plot body diagram? You have magnitude, which is absolute value of G. You're plotted in dB, that's okay. I mean, you can convert it into dB, but the peak will not change, right? It doesn't matter if you write peak in dB. It's just scaling the y-axis, okay? But not scaling, not moving the maximum point. Maximum point still on body diagram will be the same place, same point, okay? Just in dB, not in regular units. So this is practically speaking maximum of body diagram, but not always body diagrams have particular maximum, okay? Sometimes they asymptotically go up to particular value, or they start with particular maximum. So they could look like that, right? So body diagram might look like that, right? And starts at minus infinity, right? So it's starting from a particular point, never touches that point, okay? So it could be supremum, not exactly maximum. If you have monotonic function of that kind going down, for example, then you have that value of supremum, but you do not have any maximum because it's not touching the maximum ever, okay? But this point, wherever it is, it could be plus minus infinity point, it is H infinity of your system. So these are system norms, which means they define some sort of gain. And this is gain. Okay, this is the most natural way to define gain. This is like how much particular sine wave is amplified through your system. This is what it is, right? If you take particular omega here, particular frequency of your sine wave, this is by how much you will multiply it, that absolute value of G, or the particular J omega, right? Now we have some small theorem, which is kind of interesting to think about, like, why is that true? So if you have two functions in series, two serial connection of two transfer functions, the H infinity norm of the multiplication will be smaller or equal than multiplication of the norms of each system separately, which is interesting. It's like if you have some function with multiple peaks, when you multiply the maximus of these functions, you get larger value or equal to multiplication of the function's maximum. This is interesting mathematical observation, actually. When you have two functions and you multiply them, and they have like two maximum points, their multiplication will never be higher than multiplication of these two maxima. In a way, is it clear where it is coming from? Like think about any functions with maximum at If maxima are at the same point, then they will be exactly equal. So if both body diagrams have maxima at exactly the same frequency, then multiplication of two of them will have maxima which is at the same point, obviously, right? Even if you have some other local maximum, but lower maximum. But if they are in different places, which means they are having different resonant frequencies, then their multiplication will be lower. Like the maximum of the multiplication will be lower than multiplication of the maximum. Okay, this is where the theorem is coming from. Now, how you compute these norms? This is the computation part. So to compute a G2 norm, which is H2 norm of the function G, all right, you need to use that type of formula. And it comes together why I'm showing that, okay? Again, I'm not even showing you examples how to compute that, not getting into theory. Why is that? I just want to connect a few dots from what you've seen before. First of all, you've seen that expression before. Multiplication of G of S by G of minus S. What was the topic? Where we saw multiplication and mirror image of the transfer function.
The Riccati equation.
Yeah, so we saw that after we saw Riccati equation, we saw symmetric root locus, and for symmetric root locus, we used that expression and picked only stable poles on the left, right, for that particular transfer function. And since it is completely symmetrical, you have half of the roots, n roots, which are not stable, and n roots, which are stable, like n poles and n poles on the left and right, because this is mirror image of left and right, right? So you pick here only stable poles and compute residual from that function. So what is that residual? Okay, this is coming from complex functions and calculus, but I assume that you might not have heard about that before in calculus courses or complex functions courses. So here's how you compute it actually. So if you have simple pole at S0, and we are talking only about stable poles, okay? Simple pole means you have single pole at particular point. And multiple poles means that you have poles at the same point, you have multiple poles, right? So for simple pole, you just compute limit when S goes to S0, to that pole, S minus S0 times the transfer function, which is mirror transfer function, root locus type of transfer function, okay? If you have multiple poles at the same place, then it's becoming more difficult. You're computing derivatives and so on and so on. So it becomes more complicated to compute, but for computers, it doesn't matter, really. I mean, you have just function in MATLAB, which is computing those residuals for you, okay? Now, to compute H infinity norm, all you need to do is to find maximal body diagram in a way, right? But where could that be? So first of all, you can identify by hand or by computing that derivative, where are the maximum? And maxima defined by derivative equal to 0 of the amplitude. So why do I need squared here? So what I'm saying is that I want to find maxima of this function absolute value, right? So I want maxima of absolute value of G. So why I'm doing derivative of G squared equals to 0?
Get rid of the imaginary?
Hmm?
Is it to get rid of the imaginary?
No, but I'm taking absolute value, so I don't have everything is real. So I'm taking absolute value. Why not to do d of absolute value of G to d omega? And that's it. And equals to 0, because this is what Fermat theorem states, right? When derivative equals to 0, it's flat, which means it's maximum or minimum. So I can find all of the maxima and minima extrema points, and then I will pick the maximal out of them. This is the process, right? But I'm saying, no, I need actually to do absolute value squared and then derivative and finding flat points, 0 derivative. Why is that? Why do I need squared? least formally. In practice, I will just divide that into multiple points and then we'll look for just maximum points, right? This is what I would be doing. Like I will kind of divide it in point, like looking for the maximum. This is what I will do in MATLAB. But theoretically, I need to do the derivative. Y derivatives of squared transfer function, not original transfer function, absolute value. Why do we do square stuff? And returning on same principles over and over again, that you at least will have it from one of the perspectives, okay? Because you will get same kind of questions from multiple different domains. I'm trying to cover something which is coming back over and over again in multiple different domains, like machine learning and other things. When you have all of the cost functions, why all of them are squared? Like why not to do integral on y absolute value plus rho u absolute value? Why should we take like y squared plus u squared? Same thing. And no matter what kind of optimization you're doing, you always will square your function. So what is the benefit of having square?
Is it possible the denominator is negative? Or
You're taking absolute value, so it's not negative.
Yeah.
Cannot be negative. So why not just to use absolute value as is without doing square to absolute value? This is exactly the point. So you need to remember that when you are making derivative of anything, you need to make sure that this derivative exists. Okay. For absolute value, you have points where derivative do not exist. Specifically at point 0, you have function which is not differentiable. The function looks like that, like v, right? This is the absolute value function. This is what it is, right? So it's not differentiable at that point. So when you get very close to 0, you cannot even compute derivative. There is no derivative. There is no meaning to that thing. But you actually can have maximum at minimum, maximum at 0, right? At origin. So you will definitely miss it because you cannot even compute derivative there. So you don't know what happens because your left derivative will be very different from your right derivative. Like if you come in from the left and compute derivative from the left, from that side, you'll have completely different derivative compared to if you come in from the right to the same point, which means your derivative is not defined at that point, but it is defined for parabola, which is square of that function, right? Now, will the minimum move somewhere if you're squaring your signal? Of course not. This function, for all positive functions, the parabola will look like that, right? It will be differentiable and will look like that, which means it's always positive and monotonic. Any monotonic function will not move your maxima or minima. It will be exactly the same order of maxima and minima, which means originally higher points will stay higher compared to other points. Okay, you will not change the order of points up and down. Your location of minima and maxima will not move anywhere. Okay, which means you can easily do minimization of squared function and you'll get exactly the same answer as minimizing regular function. Okay, if the function is positive, of course. Okay, if the cost is positive. Same thing happening here. So we are doing derivative of the square, knowing that 0 of that function squared will be exactly at the same points as your original maxima and minima points. Okay, so we actually can do that, but now this function actually has derivative everywhere. Okay, and the idea is that H infinity norm for the G, which is G infinity norm, is just maximum of absolute value of J omega peak, whatever peaks you found. So you kind of sweep on all the function, finding all of the peaks, and then also taking that at 0 and infinity, because asymptotically it can get to supremum only at the end or from the beginning. Okay, these are the two options. You cannot have something which is going asymptotically to something in the middle. So it can go asymptotically on that side or on that side. It cannot be in the middle anywhere. Which means all you need to check is what happens for your positive infinity frequency, for zero frequency, and for all of the maximum points. Which one is higher? All right, on body diagram. So you're checking first point on body diagram, last point on body diagram, and all of the local maximum on body diagram, and finding the maximum out of all of these numbers. All right, this is your H infinity. Any questions? All right, a few properties of these norms which are useful in controls in general. So if you have stable and strictly proper G of S function, and you get some impulse response, and we'll call that delta response, right? So U equals to delta. Your Y infinity norm, which is norm of the signal now, equal to your system norm, infinity norm, okay? So they both equal to each other, which is very important observation that for impulse response, they both will be equal, okay? Same thing for the 2 norm. H2 will be equal to L2 norm in that case. For sinusoidal inputs, if you have sinusoidal input of particular frequency omega 0, Y infinity norm will be just that value of body diagram at that particular point, right? So if you send in particular frequency here, right? So this is your omega 0. This value is practically your norm by definition for sinusoidal signals, right? But Y2 norm will be infinity. Why is that? For sinusoidal input. Why is that? Why is that? Like, what is Y2 norm? So you have sinusoidal input to your LTI system. What is your output? Sinusoidal output, some sinusoidal output, whatever, different phase, different amplitude, doesn't matter. Something sinusoidal. What is norm 2 of that output? It's square root of energy. So what is energy? It's integral on absolute value squared, which is taking the plot, squaring it, computing area under the plot. What will be the area under the plot for sinusoidal signal? Infinite. It's periodic signal. So you'll have infinite energy. So square root of infinity is still infinity, doesn't matter. Okay. So obviously Y2 norm will be infinity. That's what you get. Right? Another interesting connections. Let's say now you do not have any specific input U, but you have some specific, some bounded input with norm bounded by 1 or whatever. So you have some limited or bounded input to your system, and we will call it U in general. Okay. So if U second norm less or equals than 1, which means just the power of that entire signal, square root of the energy, is less than 1, which means the signal practically is bounded by particular maximum and minimum. All right. We have relations to the outputs and output norms. All right. So we can expect that for that system, supremum on Y2 norm will be actually G infinity, H infinity norm of G, of your function. Why is that? Try to understand what is the meaning of that. So you're giving some limited magnitude signal to your system, okay? And your magnitude of that, like area under the plot squared, is less than 1, which means it's kind of decaying to 0, obviously, it has to. Otherwise, your area will grow with time. So it's signal which is you're giving some impulse or some other input, which is limited in area, then it decays to 0, and then you have output of some kind, okay? Obviously, for any stable normal system, it also will decay to 0 eventually, exponentially, right? Depends on the location of poles and so on, but it will somehow decay. So the claim is that the maximum that you can get, which means what is that thing? It's maximum on the area of y absolute value squared area, right? This is what it is. Is that thing which is maximum body diagram. It's interesting. I mean, all of these relations are kind of very interesting if you think about them. You need some time to interpret what it means, all of the things. Like what is y infinity is maximum of y, like maximum deviation of y will be equal to the second norm of the system if your input is bounded, okay? Or if maximum of your input is 1, which means maximum deviation of your input is 1. Your maximum deviation of your output is G norm 1, okay? So all of these relations are a little bit tricky. I mean, I will not prove them, obviously, but you can read more about that, about these connections. What I just wanted to show for you, it's only terminology, okay? I'm not getting into actual robust control. Now, given all these norms and all these definitions, you can define performance and stability of systems, okay? Because this needs to connect you to some sort of PBOS systems, if you remember, right? Bounded input, bounded output. And that boundedness could be defined using norms, right? Because this is what bounded means in general. What is bounded? Maximum deviation such and such. This is what bounded means, right? But now I can write it as norm less or equals than something, right? And given all of these relations, I can say, oh, the output will be bounded such and such way. All I need to compute is that norm to see how much it is bounded, if it is like finite form or some infinite number, right? And then I will know if it is bounded or not bounded. And you can think about these things as gains. So this, for example, is gain between norm 2 to norm 2 of input and output. This will be exactly the maximum point on the body diagram. It's maximum gain to the energy, like how much boost to the energy you can give by your system. That's exactly your maximum body diagram shows you what is the maximal boost of energy that you can give to your system, through your system, to your input signal, okay? So all of these relations are very important for future topics, which we will not learn in this course, okay? But if you have any questions, you're welcome to ask on that third part, because we will move to the fourth part of the robust control, which is related to frequency domain characteristics. Something that I also developed in my work before that. Some other cool stuff. Any questions? Okay. Let me stop sharing that part. Move to the next part. And now we're getting closer and closer to the original Controls 1 course. So we went through 3 different subtopics of robust control. And now we are moving to the fourth one, which is maybe less popular in general sense, but it connects very directly to what you learned in the previous courses on controls. All right, so this will kind of expand your horizon on the general control in general frequency domain. All right, so you all remember Nyquist, right? And Nyquist theorem on stability. And my claim would be that this theorem is really nothing new after theorems in math that were known at his time and 100 years before him. So he just applied regular mathematical theorem, which is a Cauchy argument theorem, to particular plot. And this particular case of that theorem is Nyquist theorem now. And I will show what are the pieces that he actually contributed and introduced, but this is a super famous theorem. And I'm not talking about sampling theorem, I'm talking about stability theorem for controls, okay? So his point was that you can plot some, I think it's called hodograph or something like that, some plot, Nyquist plot, okay? And count the number of encirclements of particular point, which is point -1. And based on that number, and based on number of open loop unstable poles, you can compute if your system in closed loop with feedback will be actually stable. Okay, so if you compute that number of encirclements of that point and number of poles in the right semiplane in open loop, you know if your system will be stable when you closing that with unity feedback, which means no controller at all, just unity feedback. Very simple system. This is what Nyquist theorem tells you. You know properties of open loop, you can learn about properties of closed loop. This is what the theorem is. Now, the plot of Nyquist is extremely simple thing. Difficult to plot by hand, but MATLAB will do that for you. Okay, Nyquist command. It will plot the entire Nyquist plot. So what that thing is real of G versus imaginary of G. That's it. So you're plotting, obviously G is complex function, G of S, your transfer function, is a complex function of S when S equals to J omega. So for each given omega, you clearly will have some complex value, right? So what you're plotting is real versus imaginary of this complex value for each given omega. So you get single point per omega. So for each omega, you'll have some points, and these points will be on a particular curve, okay? And omega is moving from -infinity to +infinity. So clearly you will have closed plot. So this plot will be kind of wiggling and closing somehow. So this is just half of the plot for positive omega, for example. Negative omega will be a reflection of that entire thing at the top for negative values of omega, okay, for negative frequencies. So you'll have some sort of circular type of shape here. Okay, this will be Nyquist plot for that particular example, which means at different frequencies, these are like radians per second, which are angular frequencies. You will get different points on that plot, and you will plot them until you get to infinity omega, which will also converge to a particular point on that Nyquist plot. Okay, I hope this is just a reminder for you and not first time that you hear that. Okay, this is Nyquist plot. And now you're looking at the number of encirclements of that plot, and you get number of encirclements, number of open loop poles, and then you know how many closed loop poles are outside of the left semiplane. This is Nyquist theorem. Okay, so let's say you have some sort of transfer function G of S. You have some sort of feedback controller. This controller could be here or there, it doesn't matter really for Nyquist theorem. Okay, and what you have is you want to check stability in closed loop of that system, knowing only stability about G of S and H of S multiplication, which means this is an entire loop here, right? You have that loop, open loop, okay? You know poles of G, you know poles of H. So you want from this poles in open loop to identify if your closed loop system will be stable, like that, via that system. So here's the Nyquist theorem, stability criterion. We will call number of unstable closed loop poles Z. this already should kind of make you wondering why Z. This is poles. Why would you call poles Z? Z is zeros, right? It's like, sounds like zeros, Z. But in Nyquist theorem, we call unstable closed loop poles Z. And if you go to textbooks and other places like that, they call it Z. Why Z? Which is coming practically from the word zeros, but they are closed loop poles. Don't remember that part. Never heard of it. Okay, we will see that in a minute. And we have number of unstable open loop poles. We'll call it P. Now it makes more sense. Okay, so we couldn't use P here. We will use it for open loop poles. But you'll see why this one is C. Minus the number of counterclockwise encirclements or revolutions around the -1 point of that function, which is practically open loop transfer function, right? It doesn't matter if H sits here or H sits here in the loop, open loop transfer function is still G times H. So you're looking on the Nyquist plot of GH, counting the number of encirclements of -1 point in counterclockwise direction, which is that direction. That direction against the clock, okay? And then your number of unstable closed loop poles will be P minus that number of encirclements. This is Nyquist theorem, okay? Sounds simple, not that simple to calculate really, but not too horrible. Okay, this is basic controls 1 course. Now, you can check closed loop number of closed loop poles outside of the area, which is in the right semiplane, based on open loop poles. Here's one example. Let's say you have some transfer function g of s. I will assume h of s equals to 1. And I want to compute the number of unstable closed loop poles. I will have these poles, MATLAB helps. Okay. Though I have even formula for that if I want to, but I will not use that. Okay, so these are open loop poles. How many of them are unstable? We have one unstable, this one at 3. This at +3, right? So it's unstable. This one is -1 plus -4, so it's on the left semiplane. It has real value, which is -1. So they are stable. But this one is unstable, which means that P equal to 1. That P here is 1. Now this is -1 point, and this is Nyquist plot of that thing. Okay, just function Nyquist on the transfer function. You'll get that plot, and you have even direction of the plot. So this plot is actually going not counterclockwise, but clockwise, which means the other direction, which means any revolution which goes that way, you count as negative revolution and not positive revolution. So how many revolutions around that point this plot has? That's already kind of difficult to do, right? You need to think like, oh, you're moving that on that curve, how many times you kind of going around that point. Kind of difficult, right? It's even for that simplistic plots. Most of the Nyquist plots look horrible. They are wiggling all over the place. And thinking about like how many times you actually surrounded that point when you're thinking about it as like radius vector moving on that plot, okay, and like how many times it like did full circle somehow, and then second circle, and maybe third and fourth, and so on. Okay, kind of tricky, right? It's not that trivial, but here you can see that it's going around in that direction one time. Like if you follow the radius vector, like you're going with that point, you're thinking about it moving one times and doing that kind of wiggling thing, then going full circle and returning from here. It will do it one time, okay, around the point. But this is -1, which means n counterclockwise number of encirclements is -1, which means that number of unstable closed loop poles will be 1 minus minus 1, which is 2. So in closed loop, that system will have 2 unstable poles. This is what Nyquist theorem states, right? We obviously want it to be 0, right? To be stable in closed loop. But for that example, you will have 2 unstable poles in the right semiplane. Okay. So why that entire thing is not that surprising? Okay, that entire theorem, what it has to do with encirclements and other things. So you have Cauchy principle of the argument, which is stating the following thing. If you have some particular curve, and we'll call that curve d gamma, so it's like boundary of particular, no, sorry. If you have particular curve, and then you have particular region for which you want to find number of zeros of that curve inside of that region, okay? You can use that type of theorem. So this is what this theorem is stating. Let's say you have particular curve d gamma, which is closed curve. Okay, you have some particular region. Let me easier to draw it maybe. So you have complex plane. Is real and imaginary. Okay, and you have some region here. It could be any region. So, and this region will be also oriented. So it's counterclockwise, and I will call that d gamma. So it's oriented contour of any kind. Okay, so this theorem states, claims something about what happens with that type of contour. And this could be any contour you want, right? Any closed contour. So we are looking for zeros inside of that area, okay? And they could be symmetrical, not symmetrical, it doesn't matter if they have conjugates or not. Some complex values. So the function could be in general complex, right? It doesn't have to be like we are using symmetrical, okay? So it's like for any generic function. You are looking for a number of the zeros of particular function, which you'll call h, inside of that contour, okay? And the contour has particular direction. So here I define a few things. So 0 will be number of zeros inside of that contour of that function, okay? That I'm checking. Some complex function, any generic complex function, h, whatever you want, okay? P is the number of poles of that thing inside of that thing. Okay, so you'll have kind of zeros here, some poles, wherever they are. And the contour can include origin, it doesn't have to, it could be anything, okay? Generic curve in space, right? And then you have that thing, which is change in the argument. So what is argument? Argument is angle, okay, in math. They don't call it angle, they call it argument. Angle of the complex function h. So h has values. So the value of h is complex number. So this complex number has angle, okay? We'll call it argument. So you are looking for the increase of that argument when you're moving on that curve. So all these points on that curve are complex numbers, right? And h, you substitute that s on that curve. Okay? So remember, we can substitute s equals to g omega, then the curve will be that axis, right? But you don't have to. You can substitute any other complex numbers instead of s, because s is just generic complex number, right? So you substitute these numbers, okay, all of these dots as you go with the contour, all right? Obviously, you get all kinds of values of h, complex values. Is it clear where I'm going with that? What I'm saying here? So let's start with that point, okay? This point is real point. So s will be plus, I don't know, 5. So you'll have H5. Angle of H will be what? So what is angle of number H of S? When S equals to 5. So 5 is clearly a real number. So H of 5 is also a real number. So what is angle of real number? Could be 1 out of 2. It could be 0 or pi, like positive or negative. This number could be positive or negative. This real number, okay? So let's say this is 0 angle, which means positive number, right? So it will have some magnitude and it will have some argument. So argument will be 0. So you'll start that argument thing with 0. Then you're doing that point, which will be 5.1 plus 0.1 G or whatever it is, okay? So substituting that thing into the H, you get another complex number, right? Whatever that number is. You measure angle of that thing, it will be some angle, whatever it is, okay? Not 0, most likely if it is complex value, right? So that way, when you kind of stepping on that function in that direction and getting the full loop, your argument, which is angle, also changing somehow, okay? So it's like some function, right? So the angle will move somehow. So this delta is by how much this argument changed, okay? How much it increased when you moved on that trajectory. It's like how much your phase changed of your function, okay? So think about like body diagram phase function by how much your phase has changed when you moved on the j omega axis, but instead of j omega axis, you're moving now on generic contour instead of j omega axis, okay? And instead of infinite one, I'm showing you finite one, which is enclosed in space somewhere, okay? So the idea is like that. So this is the theorem. This is the actual theorem. Number of zeros inside of that contour minus the number of poles inside that contour equal to 1 divided by 2 pi and the change in the argument, in that angle. This is Cauchy theorem. Now, this seems to be nothing to do with Nyquist theorem initially, right? Like, whereas that Cauchy argument stuff with Nyquist, it's like we had rational functions with poles, zeros, but they were not z pole or zero stuff. It was completely different. And we had not even zeros in the Nyquist theorems. You don't care about like where the zeros of transfer functions are in Nyquist theorem, right? So seems to be not related. But look how it is related. Here's how it goes. Actually, only a few steps. It's actually moving to the Nyquist theorem very fast. Assume that this thing is that type of contour. So that d gamma is moving on j omega axis from minus infinity to plus infinity and closes that in infinity. And pay attention that Nyquist defines it in opposite direction from Cauchy for whatever unknown reason, historical reasons, let's say, okay? So everything in Cauchy theorem, this will come with minus sign, okay, that argument, because the contour is clockwise, not counterclockwise, okay? It's already adds us difficulties in interpretation, but just remember that this contour is clockwise. Nyquist defines it as going to plus infinity first, then closing that in infinity, and then returning from minus infinity to 0. Okay, this is how he defined his contour when he proved his theorem. So this radius goes to infinity of that semicircle. And we want to know if there are any poles in closed loop in that semicircle. And we want to show for stability that there are nothing inside of that thing, right? Then the system is stable in closed loop. That's exactly what Nyquist claims, right? So here's how it goes. T closed loop for our system is G divided by 1 plus GH. Remember that? So if it would be serial controller, this would be like GH at the top as well. But it doesn't matter because we care only about that part. This is where denominator is. Stability in closed loop defined by zeros of that function, regardless if H is in the feedback or serial H controller, right? Remember that? So this function has actually numerator, denominator, and this function has numerator and denominator, right? So the poles of closed loop are defined by numerator of that function, which are zeros of that function. Is it clear? So you can think about that as this one is numerator divided by denominator, and this one is numerator divided by denominator. So these denominators actually cancel, and you get numerator of z divided by numerator of z. And numerator is polynomial of zeros, not poles. And this is where z is coming from. So closed loop poles of the system are zeros of that thing. Here's how it goes, okay? So here's how you can see it. So let's say this function is some numerator divided by some denominator. Like one polynomial divided by another polynomial. I will call them n and d, or numerator and denominator. Okay, this is your open loop transfer function. Now 1 plus that thing, which is that thing, is ns plus ds divided by ds. I'm just combining the things together. Is it clear where is it coming from? This is relatively simple development. To get G of open loop is, I will define that as numerator divided by denominator. Okay, and now I want G open loop plus 1, which is exactly what is sitting down here, right? That part, this one. So this will be 1 plus n divided by d, making common denominator, it will be d. And here you'll have d plus n. Algebra. Okay. So numerator will be d plus n. So roots of that polynomial, this polynomial and this polynomial, right? So roots of this polynomial will be your closed loop poles, which is n plus d polynomial. This is how it is defined. All right. So zeros of that thing will be your closed loop that you don't want to be here. So closed loop poles are zeros of that thing. Okay. Open loop poles are poles of that thing because they are here. This is the denominator of your open loop transfer function, right? This is how we called it. So actually your poles, open loop poles are poles of that thing, and closed loop poles are zeros of that thing. Now, encirclement of the origin by GH is the same as encirclement of -1 by 1 plus GH. Okay, so what is adding 1 to a particular function? It's shifting the function by 1 to the left, right? So instead of encirclement, actually moving to the right, actually. So if you have some particular function and you count in number of encirclements of that point, okay, you can add 1 to that point, and then it will be encirclement of that point, of -1 point, okay? Because you shifted that entire thing by 1. This is what it is. So this is what Nyquist actually used in that kind of thing. So what is addition of the argument? It's how much angle you have around that point. This is number of encirclements of that point divided by 2 pi. Like angle divided by 2 pi. 2 pi is 360 degrees, right? It's exactly the number of encirclements, right? If you divide the overall addition of the angle around 0 and divided by 2 pi, this is how many times you pass through 4 quadrants, which is number of encirclements, right? This is exactly the same thing. So that thing divided by 2 pi is how many encirclements you had of 0 point. This is what it means. But now we need to do encirclements of -1 of GH. And GH is exactly Nyquist plot, right? So number of encirclements of GH of -1 is exactly like that argument thing of around 0 of 1 plus GH. Equivalent completely, okay? This is overall idea. And then we just write that theorem as it is. So Z will be that number of closed loop poles that we want. This is the number of zeros of 1 plus GH equals P. I'm kind of moving P with other sign to the right side. P here, which is open loop poles. And then plus that argument theorem of 1 plus GH. This will be, instead of plus here, you will have minus here. And the only reason is that this contour is positive for a Nyquist and not negative. Okay, so these are kind of minor changes that Nyquist introduced to that theorem and used on that particular contour. And now we have Nyquist theorem. This is actually proof of Nyquist theorem, if you haven't noticed. So this is how you prove Nyquist theorem. You're just using Cauchy theorem and then applying that to that particular contour for that particular function. Okay. So this is how you prove Nyquist theorem. And next time we will talk about like how you drop all of that stuff and you don't need all of these encirclements to compute. And you can do that much easier. And then it's much easier to expand it also to body diagrams, which you probably never heard of, that you can check stability without Nyquist theorem. You can use stability using body diagrams. And it becomes even much easier than using Nyquist theorem. And you can expand it to multiple other domains. And you can do that for robust systems and so on and so on. Okay? Any questions? All right. Thank you.